um, how things are going. Okay, let's jump into okay, so let's continue on from last week.
You have a little bit, okay?
Huh?
Oh, sorry, I'm talking to my kids.
Oh, okay. All right. We had talked about last time the concept of a chemical reaction, and a chemical reaction requires, excuse me, kid, the products to be more stable than the reactants. Otherwise, the reaction won't happen. And very quickly, that's got to happen. Otherwise, it won't. Simple as that. And to force reactants into products where the products are more unstable, then you have to put energy into the system. And then the products are unstable and they don't last very long because they want to become more stable by going back to the reactant site. We find that a lot in things that have expiration dates. That's what that means. When you have a drug and it's got an expiration date, that means that drug is in the long term. And of course, we're being, mindful of public safety, that the product is not as stable as the original reactants, hence the date. And what that means, though, it isn't necessarily reactants it goes back to. It could go to something else. But the bottom line is the reactants are not as stable as the original reactants. Okay. When this happens, where the products are more stable, there's a fancy name for that. That's called exothermic. And exothermic means it gives off energy, and usually it's in the form of kinetic energy. Remember, kinetic energy is the energy of motion, energy of molecules vibrating and moving from place to place, all that good stuff. And usually it's measured in temperature. So if we're giving off kinetic energy, that means what?
Giving off heat as well?
Yep, exactly. So the reaction gets hot. Instead of carbon, let's put wood here. Because wood is made up of cellulose, which is carbon and oxygen. Okay, so we have wood plus oxygen. That gives us carbon dioxide and water and energy. And what happens when we burn wood? It gets hot. That means the carbon dioxide and water is more stable than the original cellulose and oxygen. Notice here that the water is more stable than the hydrogen and oxygen. Why do we know that? Look what side of the equation the energy is on. This requires energy to happen. This requires energy to come into the system before we can get hydrogen and oxygen. Now, this is how the International Space Station, this is how submarines all generate their breathable oxygen. It's taking water and in creating hydrogen gas and oxygen gas. But it requires energy because the hydrogen gas and the oxygen gas are not as stable as the original water. In fact, if we reverse that reaction, that's what fueled the shuttle. We took liquid hydrogen, liquid oxygen, put them together, formed water with lots of energy. And by the way, the temperature did go up. But the bottom line is the water is real stable compared to the individual hydrogen gas and oxygen gas. So endothermic means we put energy into the system for the reaction to happen. So energy is going in. Exothermic means the energy is going out. Okay, so we have endo and exothermic reactions. Now,
Can I ask something?
sure, always.
So when you say energy, by energy, are you also referring to heat?
Yes, it could be many forms of energy. And usually, like you said, it's usually heat. You know, like with wood and oxygen sitting together, nothing happens, right? We've got to do what? What do we have to do to get wood burning?
Light it on fire.
Yeah, we have to supply energy to
That
get
makes
it over the hump. Because remember, reactants, the bonds have to break before the product bonds can reform. So to break those bonds requires energy. So even though we give off energy here, we still have to put in a little bit of energy to get that thing going. And I'm going to talk a lot about the concept of what that means, similar to the graphs we were looking at last week. But yeah, the energy is usually heat, a spark, something like that. Okay, so right now we have two kinds of reactions, exothermic, endothermic. Okay, and now some of these you may not be aware of. Wood burning in a fire obviously is exothermic, it heats up. A bomb exploding, duh, gosh, it's exothermic. But another interesting idea is what happens when ice melts? Will ice melt by itself?
No.
Why?
You need to raise the temperature.
Yeah, and usually it's raised by sitting on the counter. It's raised by sitting in water. Same with water boiling. Water boils, we got to put heat under it. So that means it's an endothermic reaction. So whenever we have to put energy into the system, even though sometimes the energy we're not aware of, for example, we put room temperature energy into ice, because the ice is not at room temperature, we're putting energy into the system. So what that means is that solid water is more stable than liquid water, because we have to put energy into the system. Now, we mentioned this before. Temperature is a measurement of heat. It's the metric we use, whether it's Fahrenheit, Celsius, Kelvin, or Roentgen. All those are measurements of kinetic energy in a system. And those are all just different units of heat. Fahrenheit, obviously you've heard of. Celsius, you've heard of. You probably haven't heard of Kelvin yet, or Roentgen. And those are absolute temperature scales. Okay, now let's go back to that ice melting. When you put ice in your drink gets colder. The only way it can get colder is if the ice melts. Okay, it's very important. And a lot of people don't understand this, that if your ice doesn't melt, your drink won't get colder. Because when the ice melts, it requires energy. And where does it get the energy from? The liquid around it. When it pulls energy from the liquid around it, it gets colder. Okay, so we drop an ice cube in water. The water is hotter, so it has excess energy compared to the ice cube. So what can happen is the energy from the warm water will be transferred to the ice. The ice requires energy to melt. So what happens is that energy is absorbed in the process of the ice melting. Hence the water loses energy and it's losing kinetic energy. So that means the temperature goes down. Does that make sense?
So does this exchange of temperature keep going until they're both balanced, I guess?
Yes. Yeah. Basically, all the ice melts, and then the liquid doesn't get any colder because there's no ice left to melt. Because the only way the liquid gets colder is if we have ice to melt. If you start with cold water and put ice in it, you don't have as much ice melting because the cold water doesn't have as much energy to put into the ice to melt. If you put ice in hot water, the hot water has a ton of energy, so it's going to dump it into the ice melting really fast. And the hot water gets cooler to the point where there's no more ice. That makes sense?
Yeah, thank you.
A lot of people don't know why their drink gets cold when they put ice in it. It's because the energy required to melt the ice takes the energy from the water. When energy is taken from the water, it gets colder. I mentioned there were 4 temperature scales, and one of them, unless you're an engineer, you never will see. That's R, which is Röntgen. The ones you will frequently see are Fahrenheit, if you're in 2 countries of the world. That's the United States, a tiny little African country. In the rest of the world, we have Celsius, sometimes referred to as centigrade. Kelvin is a special unit. Now remember I mentioned that temperature is the metric used to determine the amount of energy, kinetic energy in a system. And the interesting thing is the lower kinetic energy of the system, the less kinetic energy or the less movement of the system. So what happens if all movement stops? That's called absolute zero. That's when all kinetic energy is gone from the system, period. That's called zero, absolute zero, and that's what K is. Now, in the past, water temperature was always measured in terms of water freezing and water melting. Water boiling. So at Celsius, water freezes at 0, boils at 100. Really nice units, got 100 units there. In Fahrenheit, water freezes at 32 and boils at 212. But those are arbitrary, totally arbitrary. We can have Tom degrees, for example. Tom degrees could be defined differently. It's still a metric of how much kinetic energy is in the system. Now, Kelvin is by definition 0 at absolute 0. Again, no movement, no kinetic energy. Okay. And R is the Fahrenheit equivalent to absolute 0. So when R is 0, it's absolute 0. And the units are Fahrenheit units rather than Celsius units. Okay, so Kelvin units are Celsius units. We just drop it down to 273 minus 273, where all movement stops. Now, you're saying, so what? Well, all thermodynamic calculations are done in Kelvin, not Celsius or Fahrenheit. All thermodynamic calculations are done in Kelvin. Now, when you get to 400, you're going to be doing a lot of calculations thermodynamically. And for example, when you put salt in water, what happens to the boiling point? Well, the boiling point is raised a certain amount, and the temperature raised is Kelvin degrees. When you put salt on sidewalk to keep it from ice from freezing, it's the same thing. It lowers the freezing point, and it's all done in Kelvin. Okay, so the definition of Kelvin is when when any substance has no kinetic energy, no molecular movement, which is 0. Hence 0 Kelvin. Now we can go back and forth between the two temperature scales with this formula here. The difference between Celsius and Kelvin is 273.15. Going from Celsius to Fahrenheit, after we take out the 32, it's a factor of 1.8. So after we take out or add the 32, and remember, Fahrenheit is always more than centigrade. Okay, so keep that in mind when you're doing calculations. If you're doing a calculation and your centigrade ends up being less than you started with in Fahrenheit, then your conversion is wrong. Okay, so Fahrenheit is always more than Celsius. It's always more than Kelvin as well. Now, Kelvin and Celsius are really easy to interconvert. It's just the difference of 273.15. So if I'm saying we have a minus 25 degrees Celsius, what's that in Kelvin? You just add 273. You want to convert Fahrenheit to Celsius, you have to take out the 32 and then divide by 1.8. And these are just a series of conversion factors going back and forth. The easiest one is this one and this one, because you're either adding or subtracting 273. And remember, Kelvin is always a lot more than Celsius. So when you're doing your calculations, when you get your end product, when you end up with your whatever the calculated amount is, and you're starting from Celsius and going to Kelvin, and your answer is smaller, then you either added or subtracted instead of the opposite. Okay, so Kelvin is always more than Celsius, no exceptions. All right, so that's chapter 3. Chapter 3 does a lot of measurement stuff. Okay, now, chapter 4 is very different. Are there any questions about kind of we've talked about this whole energy thing and endothermic and exothermic?
I have a question about the Kelvin scale.
Yes.
So when you say that the Kelvin scale stops at absolute 0, I understand that there's no kinetic energy at that point, but that scale is not based exactly on temperature, right? It's based on the amount of kinetic energy. So it can get colder than that, but it's just that there won't be any molecular movement. Is that it?
Yes. Usually we don't talk about getting colder than absolute 0. because there is no, the concept of negative Kelvin degrees doesn't exist.
So if we
What
were
is-
talking about temperature, then we would probably use a different scale.
Well, what physicists did a long time ago, they said, well, if we're looking at kinetic energy of a system, what if there is no kinetic energy, no movement whatsoever? Can things get colder than that? Well, if there's no kinetic energy in the system left to pull out, you can't get any colder. So physically, we can't go below zero either. So it doesn't matter what scale we use, when all molecular movement stops.
So like the absolute zero is the coldest it'll ever get in any point of the universe.
Yes.
All right, that was my question. Thank you so much.
And based on what we know now, okay, because we don't know very much about the universe. We know a lot, but in the scale of things, we don't know a lot. Like we don't know about dark matter and a whole bunch of stuff. But what we do know right now, today, is that nothing gets colder than 0 degrees Kelvin. Okay, but science, it's important to understand, science is a moving target. Science will change if we get new data. And right now the data says nothing will get colder than absolute zero. So our science isn't changing because we don't have any new data to change that. Okay. All right. Now, chapter 4 is on atoms, elements, and the periodic table. It is, as far as today goes, we have 118 different types of atoms or elements. And only 91 of those occur naturally in nature. The rest are made in some kind of device, a cyclotron, a collider. There's all kinds of devices that has been made to make new elements. And these elements aren't particularly stable. Sometimes they're around for, hours, sometimes they're around for microseconds. They're just not very stable. But we have gone all the way up to the periodic table in 118. I'll show you where that is in a minute here. Okay, so if we have matter, matter is composed of atoms. Once we get below an atom, the identity changes. Once we get below an atom, it does not have a unique character about it because it's broken down into subatomic particles, which are all the same. Those are, and there are many, there's like hundreds of them, but the ones that you probably have heard of are protons, electrons, and neutrons. Because when we get below an atom, the protons are all the same, the neutrons are all the same, the electrons are all the same. But once we put those together in certain combinations, we have certain characteristics because of the combination, and we call those atoms. When we put the atoms together, those are called compounds. And those compounds can be, hundreds of millions of things. Proteins, iron, wire, concrete, glass. I mean, just anything you can think of is a compound, unless it's singularly an atom. Okay. Through the many years, physicists have tried to figure out something that we can't see. What does it look like? Dalton is one of many, excuse me, many physicists that have proposed what the atom looks like, how is it put together, what are the forces driving it, etc. Right now, we've gone way past Dalton, and I'm going to talk about some of those contributions from physicists over the years. But we start with the Greeks. You know, Aristotle, thought that all matter was made from earth, wind, fire. Let's see, wait a minute. 4 elements: fire, water, air, and there's one more.
Earth.
Huh?
The last one is Earth.
Earth. Yes, I mentioned Earth too. I just quickly forgot. And over the years, we've refined that every so often. Now, there's 2 things I want to add to this brief history, is that this history is of Europeans. We have history from Asia and the Middle East. That was done a lot before the Europeans. Now, in Asia particularly, thousands of years ago, they were experimenting with chemicals. They had their own stuff going on in terms of alchemy-like kinds of things, way before the Europeans, thousands of years before the Europeans. In the Middle East, the same thing. The Asians were the oldest. Middle Eastern science was going full bore around 1000 AD. And very few people give credit to Asia and the Middle East for that early atomic physics. In fact, there's a famous chemist from the Middle East that's called the godfather of chemistry. It's from the Middle East, not Western Europe. So anyway, I make sure that you hear that from me loud and clear. Every person, what have we got on here? Thomson, Millikan, Rutherford, Bohr, all these people are from Europe. And this all happened during the Renaissance in Europe. Okay, so a guy named Faraday was fooling around with something called a cathode ray tube, which is the old-fashioned TV. Basically, you got a big chunk of glass that's hollow, and there's phosphorus that's on the flat part of the screen. And when you shoot an electron beam onto that phosphorus, it glows. And early on, we had black and white TV, so it either glowed or not glowed. And then you ended up with the black and white TV. Then they added color, which glowed in different colors, and on and on and on. But Faraday, about 150 years ago, discovered that if you could shoot these fundamental particles found in all atoms onto the cathode ray tube, it lit up. They were negatively charged, and they were considered fundamental particles. Later, they named them electrons. Millikan later on determined the charge of the electron. C is coulombs. Was a measure of charge, either positive or negative. And he just set this 1.6 times 10 to the 19 coulombs to a value of -1, just arbitrarily, because all of them tended to be that value. And Millikan had something called an oil drop experiment, which is very famous, that you'll go over in detail in Chem 400. But basically, Excuse me, that's what he determined. He also determined the mass of an electron. Now 10 to the minus 28 grams, that mass of an electron is really, really, really small. So electrons have a very high charge ratio to mass ratio because protons are +1 and they are 10,000 times bigger than an electron. So those electrons are really small compared to protons. I'm going to show you that in a minute here. Okay. Now, there was a guy named Thomson. And where's Thomson? And Thomson believed that the atom was composed of a mixture of electrons and protons, protons being the opposite of an electron, just floating around arbitrarily inside the atom with no organization. Now you have to remember, modern science is you have to retest science ideas all the time to make sure they're valid. So Rutherford, the turn of the last century, was studying Thomson's model. And he devised an experiment whereby he shot the atom with a special particle known as an alpha particle. And he found that when that alpha particle shot through a gold atom, some of the particles bounced back. Because before that, Thomson said anything can shoot through the atom without any problem. So Rutherford was saying, okay, I want to test that theory by shooting a alpha particle through gold. And this is what his experiment looked like. So basically, Thomson, it's called a plum pudding model, was expecting his particles to go right on through, 100% of them, to go right on through unimpeded. And then there's some foil here to measure those particles as they went through. So basically, Rutherford was expecting everything to be right here, which would show that Thomson's model, called the plum pudding model, was in fact a valid model. Rutherford's model, however, I should say Rutherford's experiment, proved otherwise. We're talking about like 0.5% of them bounced. And Rutherford was going, wow, what was so massive in that atom that allowed that alpha particle to bounce back? And some of them bounced directly back. Had to be something very massive in there. He came up with a concept of the nucleus, is where most of the mass of the atom is located. Because nothing except that massiveness would be able to bounce an alpha particle. An alpha particle is made up of 2 protons and 2 neutrons. And that's a big particle. When you get into nuclear chemistry, you talk about alpha radiation, beta radiation, gamma radiation. Alpha radiation is the biggest because it's got 2 protons and 2 neutrons. It's giant compared to the other subatomic particles. So Rutherford's contribution to the physics of the atom is he discovered a nucleus through his gold foil experiment. This is very, very famous experiment. Okay, so he shot this alpha particle, kind of like a ray gun, at the gold foil. And again, he was expecting everything to go right on through. Not everything went right on through. Some things are bounced. And the only thing that can bounce this big giant particle is something massive. So he was saying it had to be something collectively all together inside that atom. So he proposed that all the protons and neutrons are all located in one place inside the atom called the nucleus. Everything else is just the leftover electrons. They were somehow, in some fashion, outside the nucleus. Now, he didn't say how they're organized or whether they're organized at all. He didn't specify that. He just said the protons and neutrons make up a massive amount of mass inside the nucleus, inside the atom, and that's centered in something we're going to call the nucleus. Okay, so Rutherford went from Thomson's plum pudding model to the Rutherford model, which means it had a nucleus. So all these protons and neutrons are all inside one spot. This one spot is extremely small compared to the whole atom. If you look at a large football stadium, the nucleus is the size of a marble in that stadium. The whole stadium is how big the atom is. So the whole 99.9% of the mass of the atom is in that tiny, tiny, tiny little nucleus. And to make matters even wilder is that positive protons repel each other, but they're not repelled, they're all in the nucleus. And there's some nuclear forces called binding energy that keeps those protons from flying apart. And some of that energy is what's captured in atomic energy. Okay. So if we had the size of a marble, centimeter, you're looking at 100 meters, the size of that atom. It's huge. So that means the atom is mostly made up of nothing. Absolutely nothing, except some random electrons flying around. So when you walk out your door today, you're walking on really mostly nothing. And see, Rutherford had a real hard time selling this idea because everyone goes, how can this be? How can we form things out of nothing? And this is over 100 years ago. So there's a lot of people saying, ah, that's BS, that doesn't make sense. If you were to go out in the street today and stop some people on the sidewalk and tell them this, they would treat you the same way. There's no way people believe that most of matter is nothing. And that's what Rutherford's saying. That's what Rutherford was saying. You know, it was pretty wild stuff. And he had data to support his idea, but still, it's far-fetched. Okay. So Rutherford basically is talking about the atom. Mass of an atom and its positively charged particles and neutrons are all located in the nucleus. Let's see. And be aware that there's non-charged particles as well, called neutrons in there. The volume outside the nucleus is empty. And we have electrons running around there in some kind of fashion. Now, he did not say anything about organization, so he didn't specify organization. Later on, some later physicists talked about the organization. And because the atom is electrically neutral, the number of protons equals the number of electrons. We are calling those subatomic particles. Subatomic particles. And there are like over 100 of these things. There's muons and boson, just a whole bunch of different kinds of particles. The three main ones are protons, neutrons, and electrons. And that's what we're going to be focusing on. And then when you get into a higher course, you'll talk about some of those other subatomic particles. And you can see the mass. These are in grams. They're kind of small, to say the least. Notice the electron is at 10,000th the size or the mass of a neutron and proton. Notice the neutron and proton are very similar in size, but not equal. They are not equal. Very important. They're not equal. A neutron weighs a little bit more than a proton. Not a lot, but a little bit. And that little bit is called an electron. So when you add the mass of a proton and an electron, you end up with a mass of a neutron. So buried within that neutron is a proton and an electron. And that's the basis of a lot of nuclear chemistry. It's called transmutation. It's where we can convert one element to another. What we do is we modify the neutron and create a proton from it. Anyway, that's a whole course. Okay. Atomic or an AMU instead of saying 1.66 times 10 to the minus 24, they're saying that's an atomic mass unit. So if we look at one atom of carbon 12, it is exactly 12 AMUs or 12 U's. Now, carbon 12, we're going to talk about isotopes in a minute, is made up of 6 protons, 6 neutrons, hence carbon 12. I'm going to go into this in a lot of detail in a minute. But when we say carbon 12 or carbon 14 or whatever, that is the combination of protons and neutrons. Okay? So that number is based on how many protons, how many neutrons. The number of protons determines the element. Change protons, you change the element. Change neutrons, you change the isotope of the element. Because you're not changing protons, the element does not change name. You've probably already known this, that positives, like charges repel, unlike charges attract. So we have 2 protons inside the nucleus. They're both positively charged, so they want to repel each other. Electrons flying around the nucleus, because they're negatively charged, want to repel each other. And there's a lot of chemistry that talks about the repulsion of electrons. Things like bonds, bond angle, all kinds of stuff. It's based upon the fact that electrons want to have the least amount of repulsion from one another. When you have a positive and negative charge together, the net charge is 0. Okay, so this is the net charge. Now, if you had more positives and negatives, your net charge would be positive. If you had more negatives than positive, your net charge would be negative. I already mentioned this, that the elements defined by protons. Change protons, you change elements. Okay? And that is usually, we talk about the Z number. Atomic number defines the element. And this is really crucial. If you do anything in science, you're going to end up with different isotopes and all this stuff, and things change when the atomic number changes. There's positron emission tomography, for example. There's all kinds of various medical tests that's being done where we fuss around with the Z number. Number two, different elements have different numbers of protons. Again, change the number of protons, changes the element. Okay, now frequently, when we look at a periodic table, there are a number of, no, let's get up there. Whenever we list a element, say we're looking at, carbon. Many of you have been in biology classes and stuff. You hear about carbon-14 used for testing the age of something. You have carbon-14, you have carbon-12, you have carbon-13, etc. What that refers to is the number of protons and the number of neutrons. Okay. The Z for carbon is 6. That cannot change, because if that changes, it's no longer carbon. So what does that mean then when I say carbon-14? That means 6 plus what is 14? So these have, all these are carbon. That means it's the number of protons has to be 6, no exceptions. And that means the remainder are neutrons. So that means this has 8 neutrons, 6 neutrons, 7 neutrons. They all are carbon. Now, some isotopes are more stable than others, hence you'll find them in nature. For example, there's more carbon-12 in nature than carbon-14 by quite a bit. So you'll see more carbon-12 running around than carbon-14. Okay, so does that make sense on when you're looking at, when you say carbon-14, how many protons and how many neutrons? We're going to be doing this a lot in this chapter. Okay. The way, and I have additional.
What determines the 6 versus the 8?
I'm sorry, say again. The difference between the 6 and the 8?
Yeah.
Okay, the 8, okay, starting from the beginning, for it to be carbon, you have to have 6 protons, period, no exceptions. If it's 7 protons, it's nitrogen, not carbon. So that's the standard, boom. And if it's carbon-14, well then, what else is left over to make it 14? Well, 6 plus what is 14? 8. So that means there's 8 neutrons that make up, along with the 6 protons, to get to the number 14. So the total number of particles in the carbon-14 nucleus is 14. I'm not talking about electrons now, just talking about protons and neutrons. Okay, carbon-12, there are 6 protons because it's carbon plus 6 neutrons. Is that better?
Yes, thank you.
Okay, cool.
Is like carbon-14 chemically different from carbon-12 in any way?
Chemically, reaction-wise, no. It does act a little differently because it's heavier than carbon-12, got 2 extra neutrons. So when we're doing things like nuclear reactions, the nuclear reactions will be slightly different. But we're not talking about nuclear reactions. Carbon 14, carbon 12 do the same chemistry. Because why? It's carbon 12. It's carbon 14 because it has 6 protons and 6 electrons. Now I'm going to talk about chemistry in a minute with electrons, because the whole chemistry of an atom is determined by not by its protons, but by its electrons. So carbon 14 and carbon 12 both have 6 electrons. So the chemistry then of carbon 14 and carbon 12 is the same. Same with carbon 13. Why? Because it has 6 protons balanced 6 electrons. Does that answer your question?
Yes, it does. Thank you.
Yeah, you're welcome. Okay.
So carbon 12, 13, and 14 is really just a way of telling us how many neutrons there are.
Yeah, exactly.
Okay.
You've heard of hydrogen, deuterium, tritium? Have you heard of those?
Vaguely.
Vaguely, okay. The difference, they're all hydrogen, but they differ in the number of neutrons. Deuterium has 1 neutron, tritium has 2 neutrons. They're all hydrogen though. Because why? It has 1 proton. Okay, and again, there are worksheets. I added 2 extra worksheets under modules that give you more practice as well. And they're a little more detailed as well in this, but those would be good worksheets for you to do in addition to the chapter 3 and chapter 4 and chapter 9 worksheets I gave you. Okay, so frequently we write a shorthand way of writing an isotope. Now this is aluminum or aluminium if you're not from the United States, you pronounce it aluminium. So what does this say here? Okay, so we have I'll go to okay, so we have now this would be aluminum 27, not just plain aluminum. It's aluminum 27. Okay, so for our class, you have to say what isotope it is. So this is the isotope. I'm going to talk about isotopes in a minute here. Okay, so whenever you talk about some element, you've got to say what isotope are you talking about. Okay, so this up here, the top number will tell you what isotope we're talking about. That top number is P plus N. Now we know P is 13 because that's Z down here. The atomic number. So how many neutrons does aluminum 27 have? Well, it's got 13 protons because it can't have anything else but 13 protons, otherwise it's not aluminum. So that's a slam dunk. And because it's neutral, the protons and electrons are the same. And that means to offset the number of protons to get us up to 27, we have to add in 14 neutrons. So this P plus N is 13 P's, 14 neutrons. That gets us up to the 27.
And how do we calculate the electrons from that?
Okay, this is really important. If it's neutral, neutral means 0 net charge. That means the number of positives equals the number of negatives. Negatives are electrons, positives are protons. So if it's neutral, that means the positives have to equal the negatives. And then the question in your mind is, well, what if they aren't equal? Well, that's called an ion. I'm going to talk about that in a minute. In fact, okay, actually, what we're going to do is we're going to stop right here. I'm going to go over these examples here. Let me just summarize what you basically I just told you about that. Okay, so if the element is neutral, that means the net charge is 0. To get 0 charge, that means the positively charged protons have to equal the negatively charged electrons. That's why electrons in a neutral atom are automatically equal protons, because we have to get a charge of 0. Okay, in an ion, which we're going to talk about after we talk about periodic table, that the charge is not 0. In an ion, you're going to have more protons or more electrons. So the ion is either going to be positively or negatively charged. So I have to tell you if it's neutral or it's an ion for you to figure out the number of electrons. And I'm going to tell you, if I don't tell you, we're going to assume it's neutral. I'll try to always say whether it's neutral or whatever, but if I don't say it, assume it's neutral. Does that make sense on the electron number?
Yes, it does.
Are the protons and electrons gonna be different by just one? Like,
Oh,
could there be like 2 more protons than electrons?
yeah, you know, 4.
So how would we figure that out? Are we gonna go over that later?
Yeah. In more advanced classes, you can actually predict that. And I'm not sure we're going to be getting that detail. There's a possibility we'll get that detail. It's just, I need to see what the department likes me to go in terms of the detail. But yeah, you can predict that. Most things, I'm going to talk about this Wednesday in the periodic table. The elements, for example, in this group here, form +1 ions. This one's +2. This one's -1. This one's -2. This one's -3. This is +3. And we'll talk about that. But and anything over 3 is not all that common. There are some over 3, but most ions are ±3. Okay, so right now though, all we know is there are ions, and that means the charge is not 0, and that means there's going to be imbalance between protons and electrons. Okay, so for all the examples I'm going to talk about here, we're talking about neutral atoms. Okay, so we have oxygen. Here. (16). Okay. Okay, oxygen 16, tell me about protons, electrons, neutrons. Well, the Z number is 8, that means automatically 8 protons. And because it's neutral, we have 8 electrons. How many neutrons? Well, 8 plus what is 16? 8 neutrons. That makes sense? Now, it just says carbon. It doesn't really tell us how many extra neutrons we have. That means let's just choose an isotope. Let's just choose the most common carbon, which is carbon 12. Okay, so that's carbon, uppercase C. Now, the elements are made up of either one uppercase or an uppercase plus a lowercase. Okay, so CO and CO are not the same. CO, big C, big O is carbon monoxide, big C, little o is cobalt. So you have to be very careful when you're writing your letters, whether it's uppercase or lowercase. Okay, so carbon 12. Well, carbon has got, if we look on the periodic table, it's got 6 protons. And we're going to talk about that extensively on Wednesday about how do you know from the periodic table when it has 6. We'll talk about that. Okay, and it's carbon 12. So because the Z, or the atomic number for carbon, is 6, that gives us 6 protons. Because this is neutral, that means we have 6 electrons. And we have 6 neutrons, because 6 plus 6 is 12. Okay, let's do sodium 23. Okay, how many protons does sodium have? Well, we can look on the periodic table, and it has so its Z is 11. Okay. It's neutral, so how many electrons does it have? Well, it's got 11 electrons. And how many neutrons? Well, 11 plus what is 23?
12.
12. And that means the number up here matches this 23 here. So that's sodium 23. But we could also have a sodium 22, sodium 24. The only difference is neutrons, not protons or electrons. Are you starting to see how this is kind of falling into place? Now, the 2 worksheets I gave you, one is on neutral atoms and the other is on ions. They'll give you about 40 of these to do, with the answers on the flip side. Okay.
The
so
chapter 3 and chapter 4 worksheets that are posted with their answers.
yes, if you go to modules, let me show you. These are the worksheets I'm talking about. These guys, oops, no, this is what they look like. I clicked on it. So you've got the name, symbol, atomic number, protons, neutrons, electrons, atomic mass. And this particular one's ions. With ions, you've got to mention the charge because it's an imbalance between electrons and protons. But anyway, that's what they look like. And then if you go down, you'll get all the answers. This will give you lots of practice on that. What we're going over right now. Okay, so what has 10 protons? Well, I don't know. Let's see. Gosh, that is neon. Okay. Symbol for neon is Ne. It's got 10 protons. And we have this particular isotope has 20 neutrons. So what isotope is it? It's neon 20. 20 up here. what has 78 protons? Yep. Now we're talking about the top number now. Okay. So we're looking at platinum here. PT. Okay, it's neutral. It's neutral platinum, so that means electrons and protons are the same. And what isotope is it? Well, 78 and 117 is 195, right? Yeah. Okay, so that's platinum 195. Are we okay so far?
Yeah.
Okay, 12 protons. Well, let's see here. 12 protons. That's going to be magnesium. Okay. And it's 12 and 12, so that's magnesium 24. Ignore this here. This is page 6. Okay, and ions, as I was saying earlier, are going to differ from neutral because electrons now are no longer going to be equal to protons because ions have a charge. So what we're going to talk about on Wednesday is how the periodic table is organized. And then we're going to get into some ionic stuff. And again, we're going to go back to protons, neutrons, electrons. And we're going to do the same sort of thing again. Also, we're going to talk about isotopes. We kind of already introduced that a little bit. We'll talk in more detail about that. Okay. Now, occasionally, I'm going to have a visiting professor sit in on us. And that's because I've never taught this class before. And the department always has people observe you if you've never taught the class before. So she'll be here on some Wednesday. Could be this Wednesday, could be next Wednesday, whatever. So just, I don't know if she's going to introduce herself or whatever, but if she does, she's very nice. She's very knowledgeable. She's been teaching at the school for, I think 4 years. She's a tenure track professor. She's very energetic. She's a very, very likable person. So anyway, so that's, if she introduces herself, that's who that is, and that's the purpose of her being here, is because she's the department. Always, every school I've taught at, whenever you teach a new class, you always observe just to make sure you're teaching at the level of the class, whether it's too high or too low. They just want to make sure it's at the level they had envisioned the class to be at. Okay, so any questions about electrons, neutrons, protons before I close this?
Not at the moment.
Okay, well,
No.
go ahead. I'm sorry, go ahead.
Oh, I was just saying no.
Okay, well, go ahead and look at those worksheets, the neutral one for sure. The ion one we're going to get to on Wednesday, and if you'd like to try that, of course you can. All this material is covered in chapter 4 in your online textbook. Have you guys all been looking at the textbook?
Yes.
Okay, are you using the online one or the one I downloaded for you?
The online one.
Okay, and don't forget, if you go to Unit 0, the whole thing is there as a PDF file. as well.
I've been using the PDF one.
Yeah, I mean, you can use, I wanted you to have both anyway. So that's why I downloaded it. You can, you can print out parts of it, you can mark it up maybe you want. Cool. Excuse me. All right. So I'm going to stop recording.